Dr. Saurav Chakrabarty, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So today we will be looking at one more algorithm for divide and conquer algorithm. So we will be seeing the algorithm for finding the kth mean. So to recollect, we have three defined kind of algorithms: divide and conquer algorithm, the greedy algorithm, and the dynamic programming algorithms. We have been using the divide and conquer algorithms and seeing some examples of that. So in divide and conquer algorithm, we first break the main problem into smaller and smaller sub problems. Then we solve recursively on each of these sub problems, and then finally we combine them to get their answers. So we have seen quite a number of such algorithms. We have seen the Euclid algorithm for finding GCD, we saw the binary search, we saw the classic divide and conquer approach of quick sort and merge sort, and we also saw how to find the minimum in a set and the minimum distance among set of points. In the last lecture, we saw how to get minimum distance among a set of points in R2. So today our problem will be generalization of finding the minimum in a set of points. So let us recap the algorithm for finding the minimum in a set of points. So we had a set S which contains some n numbers, and we want to output the minimum number in S. So the most naive approach is to sort these numbers in ascending order and then output the first number in that sorted list. One can clearly see that this can be done using order n log n steps, because we need order n log n steps for sorting, and outputting the first number will take just one step. So order 1. So the total runtime for this approach will give us order n log n. Now can we do better? And the idea was to use divide and conquer approach. So we split these sets into two equal sets, S1 and S2 of n over 2 elements each. We find the minimum in S1 and S2 recursively, and then we output the minimum of these two minimums. This is a correct algorithm. The correctness of this algorithm can be seen from the fact that minimum of a set of n elements, minimum of the first element, and minimum of the second half. So now we want to ask some more complicated questions. So in general, for this particular new algorithm, what is the runtime? So we saw that while the naive algorithm took order n log n, this divide and conquer approach took order n steps. So the question is that can we use the similar techniques to obtain something better? So here is the question. We want to find the median in a set of n elements. So we have been given S, which is n numbers, and we output the median in this set S. So for people who are used to statistics or even some other economics and all, finding the median in a set of n elements is very essential problem. So what is the median? The median is basically the n over 2th minimum in the set S. So in other words, if you arrange this set in a ascending order, it is the central number. So it kind of says that what is the average in some sense, although it is not the usual arithmetic mean average, but it is some kind of an average to understand that this is the median of the halfway mark in this set. So, this is a natural question, and how can we do it? In fact, one can ask a much more general question, and that is that I give you a set of n numbers and I want you to output the kth minimum in a set S. So, k is also a parameter given to us and we want to find the kth minimum in the set S. So, if k is n over 2, that is called median. If k is 1, then that is the minimum. If k is n, then that is the maximum. If k can be anything, k can be 100. So, one can ask that what is the 100th smallest element in this set S. This can also be looked at as finding the various quartiles and so on. So, now how do you do it? Look at this set S. It is an unsorted set of integers. By looking at this set S, one cannot suddenly say what is the minimum, or in other words, even if somebody says that let k be 10, then what is the output that we want? It is not at all easy or not at all obvious. So, again just in the case of the finding the minimum, the first approach will be a naive approach, which is we sort these numbers in an ascending order and then we output the kth number in the sorted list. It is clear to see that once we have the sorted list of numbers, then finding the kth number or kth minimum is very easy. You just have to go for k steps and output the kth number. So, in other words, say if this is the set S, we just sort this list in this fashion, and after we sort this list, we can easily output the kth value. So, in this case, say if I look at the 10th object, the 10th object is 31. I mean, you can just count it and see that 31 is the 10th minimum in this set S. Now, what is the runtime of this algorithm? The runtime of this algorithm is n log n. Why? To sort this set of numbers in an ascending order, we need order n log n steps. And then once we have sorted it, then finding the kth minimum will take order k steps. So, this if you sum them up, we get order n log n, and so this is as much as we can hope for. Now comes the next attempt using divide and conquer approach. Now, this approach is a bit interesting. In this approach, we will break this problem in very small sub problems, and we will somehow combine this all these things in a very clever way. So, let us assume that S is this set given here. So, for this approach to work, we essentially need that S is a set of distinct elements. So, thus S does not contain any element twice. This approach that I will be describing, known as the median finding algorithm, can be modified to handle non-distinct set of elements, but in today's example we will be looking at only distinct set of elements. So, to start with, so we take this set S, and the idea is to split this set S into small sets of size 5. Now, why is this number 5 important? This number 5 has no special importance, it is just a constant. The idea is that to sort a set of size 5, we will need 5 log 5, which is still a constant number of steps, and that is basically the reason we split it up into set of size 5. Say for example, we start with this set and we split it up into these 5 columns. So, we take the first 5 elements and put them as the first column, we take the next 5 elements, put them in the next column, and so on. Now, one important thing to notice is that in the case of the finding minimum, it was easy. I find the minimum in various sub problems and take the minimum of all of them, we get the minimum. But in this setting, if I find the median or even the say 10th minimum in all of this setting, all of these things, it is hard for me to find the 10th minimum as a on the combined list. So, median can really be off when we are splitting up into sub problems. So, the next step is we sort it column by column. So, say we take this first column and we sort it. Similarly, we will take each of the columns and we will sort each of the columns, and thus we get a sorted list of numbers. Note that each of the columns is sorted, that does not mean there is any relation across the columns, because we have arbitrarily split this set S into 5 parts. So, we cannot say anything about how this looks like or what is the median of this set. What can be done is that we have this median of each of the columns. So, for example, let us consider the median of all these columns. So, in this set, since we have 5 elements, so we want to take the third element. So, we take the third element in each of these columns and they are the median of each of the columns. Now, can we say something about the median of the whole set by looking at the median of these columns? Answer is actually no, but what we can do is that we can sort all these columns. So, we sort these columns according to this median. So, it is like, for example, say since 10 is less than 13. So, we will move this whole column ahead of this column. Similarly, since 25 is less than 35, but greater than 19. So, we will move this whole column here. So, if we do that, what we finally end up getting is getting something like that. So, we sort all these columns according to the medians. Once we are done with this medians will help us to have some nice element, and which is the median of the medians. So, consider the median of the medians, which is the 19. So, I have 5 points, I consider the median of the medians. So, what did we do till now? We split this whole set into small sets of size 5 each. We sorted each of the small sets, we found the median of each of them, considered the median of all of them, sorted that medians, sorted the whole rows according to this median column, and then found the median of the medians. Let us take a small break now. After the break, we will see the beauty of this particular matrix. Welcome back after the break. So, before the break, we had taken this set S, split it up into 5 columns, sorted each of the columns individually, then sorted these columns according to this median of them, and then we took the median of the medians. What is the beauty of this algorithm, of this matrix? The beauty of this matrix is that every element here, say this number 25 is greater than 19. Why? Because I have sorted this median, since 25 is after 19. So, 25 is greater than 19. Similarly, 35 is greater than 25, which is greater than 19. Now, each of these columns were individually sorted. Thus, 28 is greater than 19, and similarly 81 is greater than 19, because this comes after this 19. Similarly, 43 is greater than 25 is greater than 19, and similarly 71 is greater than 25 is greater than 19, and so is 41 greater than 35, which is greater than 19, and 55 which is greater than 35, which is greater than 19. so does the lower right hand corner of this whole matrix is greater than 19. Since the 19 is acting like a pivot in some respect. Just like that, we can see that say 13 is smaller than 19, because 13 we had sorted this median row, and so 13 was before 19, so 13 is less than 19, and similarly 10 is less than 13 is less than 19. And since each of the columns are sorted, so 17 is less than 19, and similarly 2 is less than 19, and 12 is less than 13 is less than 19, and 4 is less than 13 is less than 19, and so is 8 and 5. So, the top left hand corner is less than 19. So, we can think of 19 as a pivot. If we recollect what we did in the case of quick sort algorithm, we had picked a pivot and used that pivot to look at all the points that are less than that pivot and all the points that are bigger than the pivot. And we had commented during that time that in the worst case, this pivot can be very bad. Every element can be bigger than that pivot. So, we will have something like T of n equals to T of n minus 1 plus n, and thus we got order n square. Somehow, if we can ensure that the pivot ensures that some good amount of chunk of elements is on the smaller than that and a good amount of elements are bigger than that, then that pivot can help us a lot. Similarly, here, so this 19 we have already seen that the bottom right hand corner is less than 19 and top left hand corner is less than 19. So, we can use 19 as a pivot. Say we use 19 and split this set S. So, we split S into 2 points S 1 and S 2. So, S 1 just contains all the elements that are less than 19 and S 2 contains all the elements that are less than 19. One thing to note is that all the blue points are in the S 1 and similarly all these green points are in the S 2. So, this ensures that these two subproblems or what we have found S 1 and S 2 are indeed much smaller than the original set S. So, once we have done that, what do we do? Note that S 1 and S 2 have this property that all the elements in S 1 is less than 19 and all the elements in S 2 are greater than 19. So, if we are looking for the kth minimum and if k is less than the size of S 1, then clearly k must be found inside S 1, because that is the all the elements are less than 19 are there in k, and I am saying is that the number of elements less than 19 is more than k. So, we do not have to look at S 2 at all. So, therefore, if k is less than S 1, then we can just recursively call finding the kth mean in S 1. If the k is S 1 plus 1, then we know that, see, we have S 1 elements less than 19, exactly S 1 element less than 19. So, the S 1 plus 1th minimum must be 19 itself. So, if k is S 1 plus 1, then the output must be 19, and if k is S 1 more than S 1 plus 1, then we can forget the set of all elements which are 19 and less than 19, and so we have to find out the k minus S 1 minus 1 minimum in S 2. So, the algorithm is very simple. We just found the nice pivot which helped us to split this problem or input into the right sub problems. So, this is an example where splitting the pivot, splitting this set into sub problems is the tricky part. So, let us just recap this algorithm. We have this minimum S k which outputs the kth minimum in the set of S, and what do? We first split this set S, and after we have split it up, we sort each of these n by 5 sets individually. Then let S 1 to S k be the sets of size 5, and we have this, we have already sorted it. So, we find the medians of all of them, So, it's M1 to Mk. So, T1 to Tk can be thought of as the columns that we have, and M1 to Mk are the medians. And then note that to find the pivot, we didn't exactly have to sort it in the terms of the median. We just had to find the median of those medians. So, let x be the median of those medians, and then we partition this set S into S1 and S2 by pivoting at x, and we solve it recursively. To solve recursively, first of all we partition it in S1 and S2, and after we have partitioned the S1 and S2, we do this following. If k is less than S1, then we output minimum of S1 comma k. If k is exactly S1 plus 1, we output the pivot itself, and if k is greater than S1 plus 1, we output minimum of S2 comma k minus S1 minus 1. The algorithm is kind of simple. All that we are doing is trying to find a pivot such that we can split this set S into a good sub problem. Here is the correctness of the algorithm. So, for all elements of S1, they are all less than x, and all elements in S2 are greater than x. And so, if k is less than S1, then the kth minimum is S is the kth minimum in S1, and if k is greater than S1 plus 1, then the kth minimum in S is the k minus S1 minus 1th minimum in S2. So, let us look at the running time of this algorithm. The running time of the algorithm is very interesting. So, let us Tn be the running time for finding the kth minimum in a set of size n. So, here I take the k as some parameter which can be anything. So, one can ask k to be 10, one can ask k to be n over 2, anything. So, here is the algorithm, right. We first split this set into sets of equal size. So, we get order n number of steps there. Next, we sort each of these n over 5 sets. Now, again, since 5 is a constant, to sort each of them we will take 5 log 5, which is a constant. So, the total number of steps required to sort all of them is n by 5 times order some constant. So, which is order n by 5. Then we have the medians. How many medians we had? The number of medians we have are n over 5, because one median for each of these n over 5 sets. So, we find the median of the medians, which means that find the n over 2th minimum in the set of medians. So, we get the total number of steps required is t of n over 5, and then we partition it this set into two parts S1 and S2. This also takes order n steps, and after that we recursively solve it for S1 and S2. So, this takes t of S1 or t of S2 steps, depending on what the value of k is. So, in other words, if we sum them up all of them, what do we get? We get t of size of S is equals to order n plus t of n over 5 plus either t of S1 or t of S2. Now, what is the t of S1 and t of S2? Can we get an upper bound on that? Now, since T1 to Tk are all sets of size S occur according to their median. So, note that k over 2 is basically the median, which turned out to be the pivot. So, the third element of t k over 2 is x, which is the pivot. And now, as we are drawing in the red and blue points, if y is the first, second or third element in T I, where I is the set of columns which are on the left of the median x, then all of them will be less than x, and similarly the bottom right hand corner will be greater than x. So, how many number of points here come which are less than x? The total number of points that are less than x therefore comes out to be 3 over 5 times k over 2. So, the number of blue elements that we had was 3 times 5 over k over 2. Now, what was k? K is n over 5. Since k is n over 5, so this is around 3 n over 10. Similarly, number of these green elements will be 3n over 10. Now, once the number of blue elements is 3n over 10, so all these blue elements must go into S1 and not in S2. So, the size of S2 must at most be less than n minus 3n over 10, which is 7n over 10. Similarly, size of S1 must be less than 7n over 10. So, by choosing the right pivot, we are ensuring that the sub problem that we have will be strictly smaller than the original problem, and here is the bound. It says that S1 and S2 will be both be less than 7n over 10. So, thus our recursions, which was this, becomes T of n is less than order n plus T of n over 5 plus T 7n over 10. One can see that this can be solved by induction. So, we have such an argument T of n is less than order n plus T n over 5 plus T 7n over 10, which means T of n is some constant times n plus T n over 5 plus T 7n over 10, and this can be proved by induction that T of n is less than 10 times C, whatever that C constant was, times n. So, this would imply that T of n is order n. An important thing is that why does this recurrence end up being order n? It is because if you sum n over 5 plus 7 n over 10, then that is less than n. To summarize, we find out that finding the kth minimum from a set of n elements can be done in order n steps. So, not only can we find the minimum, but we can find any kth mean in order n steps. So, this brings us to the end of the lecture. In the next lecture, we will be going into greedy algorithms and seeing examples of greedy algorithms. Thank you.